Hi, I'm Bob from Hawkswork Hardware, and in this video we're going to take a look at something which I've received lots and lots of questions about over the years. It seems to be something which is a bit confusing to lots of people, and that is the diode matrix, or just the matrix, as is used in lots of keyboards and one or two other wiring parts of the organ. So in this video I want to show you exactly what a matrix is, why we have it, why we use it, and hopefully it'll be a very simple but quite in-depth explanation, so that at the end of it, whatever your knowledge level might be now, even for a complete beginner that knows nothing about electronics, by the end of this video hopefully you'll understand what the matrix is and why we use it, and more importantly how you can use it in your own projects if you need to just connect something to a keyboard which is wired in a matrix fashion. So let's take a look and see where we go from here. Okay, so first of all, what exactly is a matrix? Basically, it's a set of rows and columns, rather like noughts and crosses or tic-tac-toe, if you care to think of that grid for a moment, where you've got three vertical columns and three horizontal rows. And that's how we refer to the connections, if you will, or the parts that make up an electrical matrix. But why and how do we get the electrical part from these rows and columns? Well, if you look at the diagram here and have a little think about this, just imagine that the blue lines in this diagram are actually pieces of wire that are just ordinary wire fixed down somehow onto your desk, say, or a piece of wood. So let's look at the rows first. If we had 8 pieces of wire stretched across our desk, not touching each other, and then just kind of fixed down with something, that would give us what we're going to call our 8 rows. And then the column shown in the diagram, imagine if that's another piece of wire running from top to bottom that's crossing all of those 8 rows, but it's suspended just a little bit above the actual row wires. So we would have effectively 8 places, which are shown as X1 through X8, where if you press down on the column wire, it would actually make contact with the row wires. So you could imagine that this arrangement would give you 8 electrical switches if we did it as we laid it out, as we've just discussed. So what happens then, of course, is that if we were to connect our column to a battery or some sort of power source, that would then become live. And because it's suspended above, or actually as it's shown in this diagram below, the actual rows, whilst the column would be energized, it would be live, the rows would not be. Okay, so that's still 8 switches, but it's not really doing anything yet. If we press down though, where 2 of them cross, so as shown in X2 here is being the junction where we're pressing down, then what happens is that column 1 wire will now touch the row 2 wire, and so electricity is free to flow from the column 1 wire through into the row 2 wire. And the same goes for all of the other row wires. If we were to press down on the X6 junction, then row 6 would become energized or live, and so you can see from this that we've kind of created a bunch of 8 switches. Now if we wanted more switches, it's quite easy to add more columns, and the advantage of doing this is that with just one column we've got 8 places where they cross, the rows and column 1 cross, so we've effectively got 8 switches. But by adding just one more wire, column 2, we've doubled that now to 16 switches, but it's only cost us, if you want, one more wire. So hopefully you can see that as we expand this, we get more and more cross points, more and more locations where we can connect our rows and columns together, but it costs us a lot less wires to do it than if we did it by just adding more rows. So going back to where we were saying, if we make our column 1 live now, we connect that to our battery again, then when we press onto a junction with column 1, then in this case we're pressing X8 and row 8 becomes energized. Now if we make our column 2 live, so we disconnect our column 1 from the battery, so that's no longer live, but our column 2 is, and now if we press X10, then our row number 2 becomes energized. Now, as long as we know which column is energized in the first place, we can very easily work out whether it's X2 or X10 that's being pressed to make row 2 energized in this example. And we can carry on with this. So if we have 3 columns, that gives us 24 cross points that could potentially be live or otherwise. So we've still now only got 8 wires for our rows and 3 wires for our columns. So we'll carry on with what we've just looked at. We'll make column 3 energized from our battery or whatever power source we're using, and if we press at X20, then row 4 becomes energized. Columns 1 and 2, of course, are not connected to anything because we're not pressing on those, and neither are any of the other rows. So far everything works just fine if we're just pressing on one cross point at a time. And if we press more than one cross point, like shown here, X20 makes row 4 live and X23 makes row 7 live. And that's fine as long as we are only pressing multiple points on the same column. The problem occurs though with this scenario if we press one of the cross points on a different column at the same time as pressing the cross point on our energized column, because as you can see from this diagram, column 3 we know is the one we've energized. That's connected to our battery or our power source. X20 is pressed, that's making row 4 energized, and X23 is pressed, which is making row 7 energized. But because X4 is pressed, that's making column 1 also energized, and we don't want that to happen because we're only supplying power to column 3, not to column 1. So you can imagine now if you were to press X1, for example, then row 1 would become energized, and that's wrong because our column 1 shouldn't be powered. So how do we deal with this situation? Well, saved by the diode. The proper name of these matrices, or matrices, both of which apparently are valid because I looked that up in the dictionary just now before I started. However, the diode matrix is so called because we use an electronic device called a diode to make certain that the last scenario where we're pressing X4, which is energizing column 1 and making things go wrong, if we use diodes we can stop that from happening. So this whole thing really is saved by the diode. So just to recap where we've got to so far before we move forward, and we'll take a look at the diode in depth now and see what it does and how we use it. But the reason we use the matrix in the first place is that if we want to have, say, 24 cross points, then we can just use 3 columns and 8 rows, as opposed to what might be a more obvious way of having just 1 column and 24 rows. And actually sometimes we do it that way. That's what a single bus keyboard is. It just has 1 column and 61 rows, but that gets quite difficult to handle. It's lots of wiring. It certainly has its advantages and its uses, but that's not what we're discussing at the moment. So let's now take a look at the diode and how we use that. In order to understand what a diode is and how it works, let's take a look very simply at what happens if we connect, or when we connect, a simple light bulb to a battery. So as we know, a battery's got two terminals, and so does a light bulb. So conveniently we can connect each terminal of the light bulb to each terminal of the battery. And ordinarily a battery has got either red and black markings on it, or a positive and negative sign, or a plus and a minus sign if you will, located at its terminals. So conventionally the plus sign is drawn in red and the minus sign is drawn in black, and the plus is called positive and the black is called negative. So if we connect these two wires, as it shows in the diagram here, to our light bulb, then obviously the light bulb lights up. But what's actually happening to make it do that? Well, electricity, which we'll call current for the purposes of this video, and yes, for the scientists who are going to argue that it works the other way, I know it does, but we're talking about conventional current here, and this is just making it nice and easy for people to understand, at least I hope it is. So the current flows from the battery's positive terminal through the red wire, and it goes into the light bulb, and then it comes out the other side of the light bulb, flows through the back wire and back to the battery, and so that forms a complete loop, or what's called a circuit. So the energy is coming from the battery, it's passing through the wires to the bulb, it's being used to make the bulb light up, and then what's left is coming back to the battery, and this just goes round and round and round all the time that both the battery has some energy left in it, and the wires are connected to the bulb. Now, a diode is a device which we can insert in this circuit, and its job is to only allow electricity to flow in one direction. So looking at this little picture here, we've shown a picture effectively of what a diode looks like, a real diode. So that's the black thing with the stripe, which is inserted in the red wire, and then underneath that is the schematic representation of the same component, which kind of looks a bit like an arrow, and the idea is that that arrow, if you will, sort of denotes the direction that current will flow through that diode. So a diode has two ends to it, and both those ends have names. The end where the current flows into the diode is called the anode, and the part, or the end, where the current flows back out of the diode is called the cathode. But the important part is that the electricity will only flow through a diode in one direction. So if we look at the top picture, we've got the cathode end denoted by that white band on the little black diode, and we know therefore that the anode end is the other side of that, and that's where the current goes into the diode, and the end with the band is where it comes back out of the diode. So we can look at the schematic representation of our little picture here. So this is what it would look like if you were looking at it on a circuit diagram. The symbol for the battery is on the left hand side, and the diode is at the top, and the bulb is on the right. So it's very, very similar to look at, and hopefully now we can understand that the power is coming from the battery, going through the diode, through the bulb, and back to the battery. But what happens if we put the diode the other way round? Well, as we said, electricity can only flow one way through a diode. It flows from the anode to the cathode. It will not flow the other way round. So, in our little circuit, if we've put the diode in this way round, the electricity comes from the battery, it flows down our red wire, it gets as far as the diode, and then it can't go any further. So our bulb remains off, no current flows, and it's effectively completely switched off the current flow through that bulb. So this is the schematic representation with the diode the other way round, and hopefully now that it's kind of arrow shape makes a little bit more sense, because you can see that the current's going to flow out of the battery from the top part of the battery, terminal number 2, and it's going to come the wrong way, the arrow's pointing the wrong way for the current to go through. So that's as it would be shown in a circuit diagram. So going back to our matrix, let's take a look at how we can use the features of a diode to solve the problems that we have when we press points in more than one column. So this is just a different way of representing the matrix that we looked at earlier. So we've got our rows 1 through 8, so they're the same as the blue wires that we had before, and we've got our first column, column 1, that's in red, and then the green sort of bottle looking bits underneath that represent reed switches, such as would be found on a pedal board. And this is in fact pretty much how the pedal boards are wired up. So if you think about this representation, the bottom C, that's a reed switch. If you activate that reed switch, that's going to connect row 1 to column 1. Okay, and when it does that, what will happen is that the first LED, as shown in this diagram, will light up, because the energy runs from the battery through column 1, through our first reed switch, which is node C, or as per the previous diagram would have been X1, and it goes along row 1, lights up the LED, runs through the black wire at the bottom, if you want, and back to the battery. So very similar to our bulb and battery and thing that we looked at just now. This is just another way of representing it so that we can understand it a bit better. The idea is, where I've put those reed switches and that column, I've done it that way round because hopefully it's easier to imagine them as being the keys on a keyboard, or the pedals on the pedal board. Hopefully that's easier to visualize than the way we did it before with just crossed wires. So we can add a second column, and we can switch our power between the two. So in this diagram we've put in a column selector switch, so currently that's set to column 1. So now we've got our red wire comes from the battery. I've added a fuse, the reason will become apparent shortly. Goes through the column selector switch, through column 1, and then we've got our switches as before. Now if we press C, or what would have been X1, the first row in column 1, then as you can see it will work just as it did before, and the first LED will light up, and all of row 1 obviously will be powered now because we've pressed that switch. So looking at our column 2 switches, we can see that there's now power on one side of the G sharp switch, or reed switch, which is fine because that note is not pressed and the switch is open, so that's not a problem. But moving forward, if we now start to play a chord, say, then we've got our C, E and G pressed in column 1, which is making rows 1, 5 and 8 powered, which means there's power to the bottom side, if you like, of the switches in column 2. So G sharp, C and D sharp, and don't worry that the notes don't seem to line up very well, but that's just how it ends up working. However, that's what happens. So when you press that chord in column 1, there's power up as far as those switches in column 2. And as you would expect, the LEDs for rows 1, 5 and 8 are lit because they're powered. The problem occurs though is when we try and play a note in column 2 at the same time as column 1. For example, if we add an octave higher C to this C chord, then what happens is because column 2 is actually at 0 volts, it's connected to the negative side of the battery via the column selector switch. So what we mean here is that the positive red wire from the battery goes through the column selector switch to column 1, but the negative wire from the battery, which is coloured black, also goes through the column selector switch to column 2. And you might just say, well, don't worry about doing that, then just select column 1 and leave column 2 not connected to anything. But in the real world, these columns are controlled by a computer, and computers deal in ones and zeros, so it can only ever be on or off. So you can't have a floating not doing anything. It has to be either connected to the red wire or to the black wire. So if column 2 is off and column 1 is on, then column 2 will be connected to the black wire. So as soon as we play this top C in column 2, you get a short circuit, which means that the current will flow through the red wire, it will flow down through column 1, it will flow through the row 5, which is our E in column 1, it will flow through row 5, it comes back up the 5th connection in column 2, row 5 in column 2, which happens to be our C note, and when we press that note we're connecting our energized row 5 to our negative or 0 volts column 2, and that's bad because obviously the current will just go whizzing around there and everything will go horribly wrong. You'll probably blow up the reed switch or melt it or something, and that's why I've put the fuse in there, because this situation would immediately cause the fuse to blow. So that becomes a problem in using a matrix for these keyboards. So what do we do about it? Well, it's back to saved by the diode, because if we look at this again now, but we put diodes in line with every key or every switch. Now the same matrix is shown here, and if we do the same thing again, we press our bottom C in column 1, the electricity flows through from the battery, through the fuse, through the column collector switch, selector switch, down column 1, through the first reed switch, which is C, through the diode, because it's facing the right way, as it were. The band is at the bottom, so that's the cathode. So the anode, you'll remember, is where the electricity goes into the diode, and the cathode is where it comes out. And this fits that perfectly. So now we've pressed C, row 1 is now energized, and the LED is lit. Also, we can play our chord like we did before. So our C chord here, C, E and G, are all pressed. Rows 1, 4 and 8 are all energized. But if we look more carefully now at column 2, because of the diodes being there, the energized parts, if you like, are only as far as the cathodes on those diodes in in rows 1, 4 and 8. The other side of the diodes, which are connected to the reed switches, are not energized. So whatever we do, whatever reed switches we press now, is not going to be a problem. So if we go back to our C chord with an upper octave pressed, now there's no problem, because whilst row 4 is energized, the electricity goes up as far as the diode, on row 4 diode on column 2, but it can't flow through the diode because it's trying to go the wrong way, and therefore we don't have that short circuit problem that we had before. Equally, at the moment, obviously, we can't tell that that top note has been pressed, but that doesn't matter, because when the computer switches to the next column, so now the reverse is true in this diagram, column 1 is not energized but column 2 is. Now is the point where you'd measure that, or all your rows again, and you would see that row 4 is now energized, and we know that column 2 is energized, so we know that it's that top C in this diagram that's pressed. So hopefully that makes a bit more sense as to why we use the diodes and how the whole matrix works. So in terms of a whole keyboard, it's exactly the same as what we've just looked at. There's just more columns, and there are usually 8 columns as shown in this diagram. So this is where we get 16 wires from that all of these matrix keyboards have. So there's 8 wires at the bottom, rows 1 through 8, and there's 8 wires at the top in this diagram, columns 1 through 8, which gives us 64 possibilities, which is why when you look at column 8 in this diagram, the notes stop at C and then the top 3 are marked X, because there are only 61 keys on a normal keyboard. So the top 3 are not used. So you can, they're usually there on the circuit board, they're just not connected to the keys because there aren't enough keys. So you can, quite often, if you just need another input for something, you can use those 3 or some 1 or 2 of those 3 as extra switches if you need to. But this is where you get 16 wires from a matrix, so hopefully it's a bit easier to understand now how all that works, and hopefully you can see that from logic it's possible by using an ohm meter or a continuity meter or a diode test meter or something along those lines anyway, you can easily check what the different wires do. And I say easily, it's not super easy, but it's not rocket science either. It's simply a matter of being logical. So what I'm going to do now is I'm going to include a clip of video where I went through and did exactly that and identified all of the rows and columns on a pedal board. This is actually from the DCS 300 rebuild video that I did. So if you've seen that video, you'll have seen this clip already, but if you want to watch it again, obviously you can. So I shall put that clip in now, and you can see how, from a logical perspective, we can work out what these different connections are. So thanks for watching, and enjoy the next clip. Okay, so we're going to take a look at this pedal board now and work out how we're going to connect that up. So I have here the cable that we looked at just now that was in the organ. I've removed it from the organ and I've plugged the end of it, the other end of it, into the pedal board, as you can see. And this is the end that we're left with. So we've got, it's a 16 way, I think, 2, 4, 6, 8, 10, 12, 14, 16. Yep, it's a 16 way connector. And we've got 32 pedals. So obviously this is another matrix. And we've got a whole bunch of wires going on here, and I haven't got the first clue which wire is which. So what we need to do is to figure out which are the common lines, of which there should be 4, and which are the rows. So there should be 8 rows and 4 columns, which gives us our 32 notes. And then once we've identified them, we will be connecting them up to this matrix, system 1 matrix keyboard interface. So there's our 8 row connections along the back and our 8 column connections along the front, although we're only going to be using 4 of them. Having said that, we're going to cheat a little bit, because that leaves us 4 spares here, and I'm going to use one of those, or possibly 2 of those, for the toe pistons. So that's a handy way of just using up the extra inputs that we've got available without having to use another interface board. So we've seen these before, so let's move that out of the way and look at what we're trying to identify here. So we're going to have 4 columns amongst these wires, and we're going to have 8 rows. So where it's got R1 through R8 here, that's our rows, and we've got the same across here. That does not mean that there are 4 separate sets of 8 wires. It means that there's one set of 8 wires which inside the pedal board will connect to these different columns when you press the pedals. So we're looking for 8 wires plus these 4. So we need to identify 12 wires out of this lot here. And I don't particularly want to take the pedal board apart, because if we look at the pedal board, the top of it here, it looks like it's been remade out of MDF, and the corners of it it hasn't stood the test of time awfully well. It's a bit bashed and battered, and I don't want to take it to bits. This bit's split. So we're going to identify this logically and electronically. So what I'm going to do is I'm going to hold down the first pedal, and then I'm going to measure the resistance between all of these different inputs here until we can identify that first pedal. Then I'm going to do the same with the second, third, fourth, fifth and so on until we've identified the first 8, and then they will be our 8 rows, which will just repeat along the keyboard or the pedal board, and then we just have to find the next 3 columns. So the way I'm going to do that, obviously I've only got 2 hands and I need to be over at the bench identifying the cables, but what I do have here is a little plastic lamp holder that happens to be exactly the right size, that I can just pop it in between the top of the pedal and its rubber thing there, and it pops out, which isn't overly helpful. Let's try that again. So I can just pop that in there, and that will hold that pedal down in the optimum position. So now that we know that our first pedal is held down, let's move our cable into shot. So we're going to do like we did before. I've got the meter with these 2 sharp needle probe thingies on the end of it, and I'm going to put one of them. So let's start with the black one. By the way, these, just to make this obvious, these have diodes on them. Each one has a diode on it, like that. So obviously we need to measure the positive lead to this end of the diode and the negative lead to that end, otherwise if it's the other way round we're not going to measure anything. So what we'll know at the end of this is that the columns are the ones which the negative lead or the black lead is connected to, and the rows are going to be the ones that our red lead will be connected to. So randomly starting, or kind of, if I can get this in shot, it's a bit tricky because the cable's not really very long. Anyway, so let's just start with, I don't know what the numbers are, 1, 2, 3, 4, whatever. It doesn't really matter as long as we identify them. And up the top here, I've made like a little representation of the plug. So that's kind of that, if you like. Those are the holes I've represented up here. So if we pop the black lead into the first one, and we know the pedal's held down, the meter is on resistance, so we will just go through and check all of the other inputs or other connections here until we find one, if we do find one, that connects to this particular hole that this one's plugged into. So if we start with that, what we're looking for is something on the meter here to change. It's not going to beep, it's not going to read continuity or a continuous short or anything like that, because we've got these diodes in the way. So it's going to read probably 600 or 700 when we find the right hole. So working from there, let's just work our way down. So nothing there, nothing there, nothing there, nothing there, nothing, 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 no, 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 and no. So okay, so that was wholly unsuccessful. So let's work our way. We can either go left, right along the plug, or we can just work our way down one side. So let's work our way along one side just for the hell of it. So let's do that again now. So basically we're going to try putting the red lead into all of the empty sockets or holders or holes or whatever you want to call them, and see until we get a reading. So nothing so far. Nope. Okay, so the next one down, we do that again. Nothing. Nope. quite a tedious process, but not as tedious as taking all the covers off of that pedal board. And there we go. Right, so we can see we've got a reading on the meter now, 655, so we know that we are reading across a diode. So we have got the red lead in the bottom left hole and the black lead in the third one down. So what I'm going to do now is just make a note that the bottom left one here, we've got that as C1, and it's the third one down, so that's note number C1, by the way, and the third one down is our negative, which we expect to be actually the column, because if this is C1 is probably our first row through the diode and through the first column, so the one that the negative lead is on is going to be the column, so that's probably our column 1. And this C1 I've got here is, I suppose, probably more correctly should be marked as R1, but it may not be. Let's just make certain and prove that. So what I'm going to do now, if I can do this without it all sliding off the bench, is to remove that little plastic thing like so and release the pedal. So now the meter goes back to 0. So now we do the second pedal along. So we want to find R2 now. We think C1 is this third one here, the black one. So I'm going to leave that black lead where it is, and I'm just going to move the red lead and see if we can find the second pedal. And just being fairly logical, it's likely probably to be the next one, one of these adjacent to it. So the one to the right, and yes, there we are. So the one to the right appears to be row 2. So if we move that up there, obviously now we get nothing, but if we now check the next pedal, so that's putting down that one, and that's row 3, so that's confirmed. And this is how you do it. It's pure logic. You just keep working your way along the thing until you find the connections that we're looking for. So I'm moving that to what I think is going to be R4, and move this up to the next pedal. Oops. Well, it doesn't want to stay in there, but 1, 2, 3, 4. So if I hold 4 down, you can see on the meter that we're getting a reading there. So that's fine. So we know that that is row 4. And there's a good chance that the next one's going to be row 5. So go back to the pedal board. 1, 2, 3, 4, 5. Yes, it is. So there we are, row 5. Move it across to there. So that's going to be probably row 6, which it is. And then the next one up over there we hope is 7. So just mark that in, row 6. That we think is going to be row 7. And it is. So mark that in. And then move that across. Hopefully that's going to be row 8. So where are we? 5, 6, 7, 8. And it is. Okay. And we know that that's column 1. So what we want to do now is go back to where we started, really. So we want to go back to row 1, which is the bottom left. But now we need to find column 2. So our 9th note, 1, 2, 3, 4, 5, 6, 7, 8 rows, we go back to row 1 on column 2 is going to be our 9th note. Okay, so if we count 9 notes up the keyboard, pedal board, so 5, 6, 7, 8, 9, we want to hold that note in. So retrieve our little plastic thing that escaped, which is easier said than done because this wire's in the way, but there we are. So 5, 6, 7, 8, 9 is that one. So let's pop that in there. There we are. So now we know that the red lead is in our row 1 position. So now we've got to start moving the black lead around to find the second column. So not that one, not that one, not that one, not that one, it's that one. Okay, so it's third one down on the right hand side, which makes sense. So that is column 2. So all we need now is to find column 3 and 4. So that's going to be 8, that's going to be 16. So the 17th pedal will connect row 1 to column 3. So let's hold down our 17th pedal. So that was 9, 10, 11, 12, 13, 14, 15, 16, 17, which is slightly harder to get to because it's covered up. How did we do it? So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17. So it's that E. I wonder if I can do this from underneath. Perhaps. It's not going to be as easy, I don't think. There we go, that worked. Okay, so what we're doing now, we're holding our 17th pedal down. So we're looking for row 1 connecting to column 3. So again, we leave our row pin in and we move this one up. And hopefully, yeah, logically, it's that one there, column 3. And so there's a very good chance that that's going to be column 4. So let's just pop that across to there and check this out with pedal 32. No, it's not 32, is it? It's 24. 31, 30, 29, 28, 27, 26, 25, 24. And yes, there we are, you can see on the meter. So that is our 4th column, column 4. So that is how you find out what the wires are on a keyboard or a pedal board that you don't have a connection circuit diagram or list or anything for. It's simply a matter of just logic, really, as you saw by the way we've done this. If this was a keyboard, it would not have 4 columns, it would have 8. So all you would need to do, at this point you'd have done the majority of it, you've just got to find the last 4 columns. So you'd hold down the next key, so that's going to be number 33. If there was a 5th column, that would be 33. Hold that one down and then you'd find the 5th column. And the same for the 6th, 7th and 8th. So it's that simple, really. Lots of people have asked how you find what the connections are, and that's how you do it. So all I've got to do now is figure out which ones of these, or which wires go to which pins left and right, because obviously they all run across that. It looks like they run across both, but they don't. So I've just got to figure that one out, which I shall do by taking the plug to bits. And I won't bother doing that on camera because this is kind of unique to this particular pedal board. Anyway, once I've done that, I shall strip this wire back and I will then connect the relevant wires to the relevant connections for the 4 columns and the 8 rows, and then the pedal board will be done and working, and that's all there is to do for that. So probably not going to do that on camera.